Welcome to The Explainer. So today, we're going to look at what I consider to be one of the most fundamental mysteries of our universe. I mean, have you ever wondered why we can predict a solar eclipse centuries from now, down to the exact second, but we can't reliably predict the weather in your own hometown just 3 weeks from today? Or why the stock market constantly, and I mean constantly, defies the most advanced supercomputers on Earth? Well, it all comes down to a fascinating mathematical concept called Lyapunov Divergence. And today, we're going to watch the forecast horizon inevitably close. Okay, let's dive right into this. Can infinite technology really buy us infinite foresight? We kind of all have this inherent bias, this underlying belief that if we just build incredibly precise thermometers, if we launch thousands of new satellites, and if we build quantum supercomputers that can crunch more data than ever before, we will eventually be able to predict the future perfectly. We tend to treat a bad forecast as just a hardware problem. But as you'll see, the mathematics governing our world tells a very, very different story. Section 1. The forecasting illusion. The core issue here lies in the very nature of chaos itself. In a chaotic system, two states that differ by an immeasurably small amount don't just drift apart slowly over time. Actually, they drift apart exponentially. This isn't just some glitch in our software, and it's definitely not a faulty sensor. It's a rigid mathematical reality baked right into the fabric of nature. When you're dealing with chaotic dynamics, that exponential drift actively ruins our predictions, completely independent of how sophisticated our predictive models are. Section 2. Inside the Lorentz system. To see how this actually works, we can look at the classic three-equation Lorentz system. This is going to be our testing ground, running in its chaotic regime where the system parameters are precisely set. Sigma equals 10, rho equals 28, and beta equals 8/3. Now, imagine comparing two trajectories, trajectory A and trajectory B. Think of these as two separate weather forecasts. They are identical in absolutely every single way, except for one microscopic detail, an imperceptible 10 to the negative fifth perturbation in the starting value x0. That is an error of 0.00001. It is far, far below any realistic measurement precision we could ever possibly achieve in the real world. Yet, this tiny, totally immeasurable seed of error is all it takes to absolutely destroy our forecast over time. Let's see why. The ultimate mathematical villain of our story is the Lyapunov exponent, represented by the Greek letter lambda. By definition, this is the largest exponent determining the rate at which two incredibly close trajectories exponentially diverge in a chaotic system. Think about the math like this. The distance between our two nearly identical starting points grows over time, and it's roughly equal to the initial error multiplied by the constant e to the power of lambda times t. Simply put, the bigger the lambda, the faster your tiny error explodes. Section 3. The speed of chaos. Let's track the timeline of this error's life cycle by its log distance. At point 1, time 0, we start with that tiny 10 to the negative fifth error. Almost immediately between time 0 and 15, we hit a linear ramp on the log scale. This represents a violent exponential divergence. And get this, the slope of this line is the Lyapunov exponent. For our Lorentz system, lambda is approximately 0.9. What that means in plain English is that the distance between our two trajectories grows by a factor of e, which is almost 3 times larger every 1.1 time units. The error is just ballooning utterly out of control. And then, as we keep going on the timeline, we hit point 3, where time is greater than 20, the plateau. At this stage, the trajectories saturate at the attractor's diameter. They are now just completely uncorrelated points bouncing around the system. Think about what that actually means for a second. All of that initial condition information, that highly precise data you carefully fed into your supercomputer, it's gone. Completely gone. Beyond this forecast horizon, literally no fancy predictive model can outperform simple historical climatology. The starting information has been totally obliterated by the chaos. Section 4. Tech versus exponential growth. Let's see what happens when our human engineering precision goes up against the Goliath of chaos. Imagine we throw billions of dollars at our sensors, and we drastically improve our measurement precision by a massive factor of 1,000. That is a huge technological leap, right? We've shrunk that initial error down by 1,000 times. Common sense says we should be able to see way, way farther into the future. But here is the brutal forecasting arithmetic. Because of that 0.9 Lyapunov exponent, a massive 1,000-fold increase in measurement precision buys us, well, a measly 7.7 more units of time on our forecast horizon.
You do 1,000 times the work, you spend billions of dollars, and the math, specifically the natural log of 1,000 divided by 0.9, spits out just 7.7 units of extra foresight. No way around it.
So the absolutely crucial point here is perfectly captured in this quote from our source material. Exponential error growth defeats polynomial effort. It is a massive emotional gut punch for forecasters everywhere. Chaos will always, always outpace our technological upgrades. You literally cannot build a thermometer precise enough to beat an exponential function.
Section 5. Rules for a chaotic world.
But look, we can't just give up and stop making predictions entirely. We have a world to run. Even if we can't defeat chaos, we can measure it to know exactly what we're up against. Forecasters can actually estimate the Lyapunov exponent lambda directly from real-world data using specific algorithms like the Rosenstein or Kant's algorithms. And practically speaking, they apply these algorithms after a mathematical process called time delay embedding. This essentially helps reconstruct the dynamics of a system from just a single time series of data. In short, we map the chaos.
Knowing what regime you're in dictates your entire strategy. If your estimated lambda is greater than 0, you are in a chaotic system. The forecast horizon rigidly closes. Your best strategy? Stop trying to predict exactly what will happen far into the future. Instead, invest heavily in short horizon accuracy and rely on probabilistic statements. But on the flip side, if your lambda is 0 or less, you have regular dynamics. The horizon is only limited by noise and model error. This is a fundamentally more optimistic regime where better technology and faster computers actually do buy you a much better view of the future. So we've explored the hard mathematical limits of prediction and how the Lyapunov exponent dictates what we can and cannot know. My final thought for you to ponder is this. If the forecast horizon rigidly closes in chaotic systems, outrunning even our absolute best technology, what unpredictable limits are hiding in the models you rely on every single day? Whether it's the financial markets, global supply chain logistics, or even just your weekly weather app, where is the Lyapunov Divergence quietly closing the horizon on you? Thank you so much for joining me on this explainer. Keep asking questions and keep exploring the fascinating limits of what we can actually know.